First thing I want to do is return back to Power Series Part B, and this weird question at the end. Someone shot me an email and said this is not working. I'm going to do two versions of this one. So let's find out what its radius and interval of convergence is. This 2x is going to cause a problem in the second one. This is the first version. So it's going to be the limit as n tends to infinity of n plus 1 factorial, 2x take away 1 to the power of n plus 1. And on the bottom, n factorial and 2x minus 1 to n. Now the cancelling is not that big a deal, actually. This guy and this guy cancels. What you're left with an n plus 1 factorial cancels with an n factorial. What you're left with.
And n plus 1 on the top.
Agreed. Now, typically you can ignore this term. And if you make this go infinite, something really weird happens. Isn't it just brute force that the answer to this is infinity? Right, so it's kind of weird already. And infinity is bigger than 1. So that means that this power series essentially diverges. So far, so good. But it still has an R and it still has an I. And you might think, but it diverges, that can't be true. Well, its radius of convergence is 0. Does that kind of make sense that if there's R is 0, you don't have any interval? But the interval of convergence technically exists. It's just a single number. What single value of x will this power series actually exist? There is one value of x that this power series exists for. What value?
1/2.
Yeah. And so your answer to the interval of convergence is, it's not really an interval, it's just a single value of a half. Does that make sense to a really weird question? Now, they didn't give this version, but I want to show you what would happen if you mucked about with this series in a quite significant way. Let's stick the n factorial on the bottom. That should make a difference. And we're going to get the limit as n tends to infinity of an plus 1 over an. That's going to be the limit as n tends to infinity. And we get this guy over this guy. And then this fella over that fella. And when you do the cancelling, do you see the n plus 1 now ends up in the bottom? And when you cancel these, you get a 2x minus 1 left on the top over an n plus 1 on the bottom. Now, the top doesn't really matter. You can pretend it's 1. But would you agree that brute force, this ends up being 0, no matter what the x is? And this is a different special case. Wait a minute, it converges all the time. Right, doesn't matter what x is, it converges. It still has a radius in convergence and it still has an interval of convergence. Its radius of convergence is now infinity. Do you see it's different from this one? It's the exact opposite. The R is forever, right? Any value you like. And what do you think the interval of convergence is? That's the values of x where this series actually converges. What do you think it should be? If something converges all the time, what values of x's would that be?
Negative infinity to positive infinity.
And that is the second special case, right? Most of the time, don't you actually get a number? R is 5 and it's from -5 to 5 or whatever it might be, right? But not in this case. That was a weird version of 5. So now I'm gonna have to put that somewhere where I'll find it. There we go. Now, let's look at power series as functions, which is essentially what 11.9 is to do with. And these guys you treat as already true. You don't need to prove them, you use them. And we're going to look at creating power series for other fractional functions. And the trick, for the most part, is to do with substitution. That's a very useful technique and to make this happen. The algebra of these questions can and is going to be really ugly. So it's almost like you only get one example of every situation. So everything is fresh. Everything is new. So let's take this guy. I want to get a power series for him. And when I'm finished, it's going to be a power series using sigma. So the first thing I'm going to do is I'm going to rewrite this guy like that. Are you happy about pulling out the 6? Now, that guy is very like, oops, this one here. Would you agree? That guy is very like this one. Now just think substitution. Think about what would I need to replace this x here by to make it that guy? And the answer is, oh, if I made this x squared, I would get this guy. So if you make this x squared, don't you make this guy x squared? So what you have is 6 times the power series of this fella, but the x replaced by an x squared. So it's going to be x squared to the power of n.
I thought that the 1/1 minus x was the one that didn't alternate.
Yes, it is. You're right. And I made an oopsie, which I'm now desperately trying to fix. But I'm glad you noticed it. I wrote this back to front. Let me do those guys again. That fella is the +1. I'm pretty sure I was distracted when I was writing them down. There we go. So, well, a little hiccup here, same idea, right? 1 minus x squared is this guy with an x squared replaced. That is still correct. Now, x squared to the thing becomes that. And this 6 comes inside. So you get n equals 0 to infinity, 6n to 2n. We now have power series with that function. Let me show you a different story. That one. It's not quite the same as this guy. Do you notice that the bottom is x, not x squared, but the top has got powers of x. So let's see how that one would work. You would do 6x cubed with that guy. I guess what you're trying to do here is isolate something that looks like one of these two guys. Now, in this case, that's a perfect match, right? I don't need to do anything else. I can just do a 1-for-1 swap. So we now have 6x cubed and the power series. But we need style points. And when you do power series, you want the whole thing inside a single sigma. So that 6x cubed has got to come inside here. I probably wouldn't normally write this line, but I have this time. Is there anything we can do to make this look a little prettier?
Change it to 6 times x to the power of n plus 3.
And now you are done.
Could you, for more style points, change the starting value of n to 3 and just have 6 times x to the n?
You could. And it's correct, but don't, because I think you might screw up WebAssign. I think WebAssign only recognizes it in one form. Yeah, it's called changing the center, essentially. Now, let's put the package together. Suppose you got that guy. He's a little bit of A and he's a little bit of B, right? But we still want to get his power series. Based on what I've already done today, what would be the first stage in this process? How would I rewrite this fraction to get us closer to the answer?
Remove the 6x squared.
Agreed. Now, this fella here, would you agree this fella here is in the family of one of these two? Right? Would you agree this guy belongs to one of these two? And would you also agree it's the top one? What substitution will I use for this one then? What will I replace the x with now?
X to the 4th.
Agreed. Are you happy about this guy is that one? Have you seen enough of them that it becomes a kind of familiar thing? What I'm now going to do, and I'm taking this nice and slowly, a lot of you can certainly skip a couple of these lines. Would you agree that that's just a better way of saying it? X to the 4 raised to the power of n. Oh, let's do it in one go. If you bring this 6x squared in, won't you get 6x to the 4n plus 2 when you're finished? Do you see we're beginning to develop a process that allows us to find power series, right? Infinite polynomials, that's all a power series is, for fractions. Now, you can't do it for all fractions, but at least we've got a process for some of the simpler ones. So let me add a very minor, but very serious problem. This is very like question 1. All I've done here is put in a 3 where a 1 should be. And sometimes the simplest change causes the biggest trouble, because neither of those guys look like him yet. This thing has got to look like a 1 over 1 plus so many x's, right? That's it, right? 1 over 1 plus and then an x thing. And right now it's 1 over 3 plus an x. I guess the x is nice, but that's not what I want. Don't you need to have a 1 here? That means you're going to have to do some weird algebra. Are you happy with what I just did there? I have pulled out a common factor of 3 when you normally wouldn't do that. Don't you normally pull out common factors because it makes the answer nice? You never pull out a common factor to make it worse. But nonetheless, I need that. I'm now going to call this 1/3. 1 plus 1/3 x. If you look at our two guys here, do you recognize that this fella belongs in that guy's family? Right, it's the 1/1 plus x family. So this here becomes sigma n equals 0 to infinity. Now I'll get the right one, a -1 to the n. And what do I replace the x by for this fraction? What do I replace the x by in this fraction?
1/3 x.
1/3 x. We're about 50% done here. God, that's ugly. And yet we have to try and make it style points pretty. Any suggestions about how to rewrite 1/3 x to the power of n? Kind of remembering that you want x's to be on their own as a kind of goal.
We could pull out the 1/3 from the x, and then because you're going to multiply n at 1/3 anyways, just make it 1/3 to the n plus 1.
Right. You're quite right. I'm just doing it in 2 steps. Are you happy with this fella being that fella? Now, do you notice this little third here? Let's bring him in, like Will just said. If you bring this guy in, won't this just turn into an n plus 1, right? A third to an n plus 1. So we would have n equals 0 to infinity, -1 to the n, 1/3 to the n plus 1, x to the n. Or that. Would you agree that 1/3 to the n plus 1 is the same as what I just wrote down? Visually, I don't have a problem with that. I'm quite happy with both answers. I have no idea what WebAssign does. Sometimes it does both. Sometimes it's funny and it only wants this one or it only wants that one. I guess you'll find out when you do the question. But bear in mind that this is the same as that, right? So it's not like you've done anything wrong. It's just you might have to play about with how does WebAssign want me to write it.
I have a question with this. When I first saw this problem, my first instinct was to write it as 1/1 plus x plus 2. Just have the x plus 2 as the
That's
x and then
interesting.
substitute that in. I mean, you get it. The answer is definitely written differently from this because it ends up as sum from 0 to infinity of -1 to the n and then x plus 2 to the n. Is it still right?
Mathematically, it's still right, and I guarantee WebAssign won't like it. What you've done is we're doing a power series, which is actually has a fancy name. They're called Maclaurin series. They're power series, but they're called Maclaurin series. And Maclaurin series have x's in them.
Mhm.
The one that you just described, the x plus 2 version, which is
Taylor
totally
series?
mathematically, is called a Taylor series, right? And it's correct, but I'm pretty sure WebAssign won't like it.
All right.
I think that's why WebAssign says give your power series representation centered at x equals 0.
It does, doesn't it? Now I'm looking at it. So that's their way of saying Maclaurins without using the word Maclaurin. Let's see. Now we've done that one. Right, let's try this one. This is a version of 3. We got that guy. It's not unlike the one I just did. So let me put that one on the screen for you. Right. Can I use what happened here to help you with this one? Any suggestions for what my next line over here is going to look like? You got this guy. What did we do? Come on, I'm getting old here. I don't have many years left.
We could take out the 2/9.
Oh, you okay? I'll write it like that. Okay. Agreed. Like you said, 2/9. We cool on that? Now, what's the guy he belongs to? Would you agree he's in the family of the top one? So that means the X is going to be replaced by 1/9. So it's going to be 2/9 sigma n equals 0 to infinity. Replace the X with that guy. This fella, X to the 9, 9 to the 9, I would write it like that. But you could write it as 1/9 to the power of n if you like that. When you bring this fella inside, you end up with that. So what we're really doing, well, the way I'm seeing this anyway, is what you're really dealing with is algebra, right? You're trying to find algebra ways of taking something that really doesn't look usable and converting into a really ugly version of itself. But at least that ugly version can now be used. And that's the skill on recognizing what you need to do to make the thing work. So let's move up the food chain and see what they're going to get us. Oops. Let's try that again. Almost wrote sigma there by mistake. I have an x squared. I have an x to the 4 plus 81, which, if it helps, is the same thing as 81 plus x to the 4. Okay. The bottom's not right. That 81 ain't good. Agreed? That's the problem. The x squared's not a big deal. We can deal with that anytime. So I'm going to pull it out as a common factor. You happy with that weird common factor trick? Again, you probably don't need this line, but I'm putting it in anyway. Can you see this guy is now, as ugly as he looks, doesn't he belong to this family here? So what you've got to do is essentially replace this x with that mess. So it's going to be -1 to the n, 1 over 81, x to the 4 raised to the power of n. X to the 4n. Well, I guess I don't like fractions. Maybe I should phrase it that way. I like to write it that way. So I don't have 1/81th to the power of n, just call it 81 to the n on the bottom. And then bring things inside to finish off the style points. Guess you don't need the brackets, but I put it in there. This is correct. This is a good answer. Let me show you another answer. Where the heck did that come from? I had 81 to the n plus 1, but now I've got 3 to the 4n plus 4. What the heck happened?
You can rewrite 81 as 3 to the 4th.
Right. Agreed?
Multiply.
Now, I have no problems whatsoever. As far as I'm concerned, that's the right answer. But as far as I'm concerned, isn't that also the right answer? And if you're just being awkward, couldn't you have done a 9 to the power of 2n plus 2 if you felt like it? It doesn't mean that the power series is essentially different. Isn't it the same power series with slightly different flavors of itself? Right? It's still the same guy. I would assume that WebAssign's looking for the first one, but you know, who knows? We WebAssign might be using that one. Any questions so far? Are we getting used to the fact of this weird algebra that we need to do to take a fraction and deconstruct it in such a way that it can now look like one of these two guys so that we can get a power series for it? Right. That's pretty much in a nutshell what I've been doing today. And we've only got to question 4. I'm not going to do much with 5. Because you all get your own version of it anyway. Isn't question 5 pretty much ready to go? Doesn't this guy, right, this fella here, doesn't he belong to this family here? So won't I just replace this x with a 3x squared and off we went? So not all questions are difficult. Doing the next fella. This is a version of 7. Would you agree that one is also now ready to go? Isn't this guy a version of that fella? Okay, so whoops, that's one piece of the types of questions that you're going to be asked over with. Now we're going to do something a little bit different. Suppose I have a power series. Maybe I got it from one of these fractions. And it looks like this fella here. Take a nice simple one. Now, if I write this guy out in full, is 3x to the 0 plus 3x to the 1, right? Plus 3x squared plus 3x cubed for eternity, right? Right, which I guess I'll write down as 3 plus 3x plus 3x squared, 3x cubed. Oh, bless you.
Oh, sorry.
That's fine. Can't help sneezing. Oh, do you know that there is a poem in Scotland about sneezing? One's a wish, two's a kiss, three's a disappointment, four's a letter, and five's something better. So
I've heard a
whoever
slightly different version of that.
you did, is it repeatable, Tim? Because I know your ancestry.
No, it's repeatable. It's the same thing.
Okay.
There's just no disappointment.
Oh, so you lost it on the boat over. You lost one of the phrases. Right. So whoever sneezed is due a kiss, but I'm not giving you it, so forget it. So it'll have to be somebody else you'll find. So back to this guy. God, I'm easily distracted, aren't I? Forgotten where we are. Right, back to this guy here. I wonder what its derivative is. Well, if you write it down as a power series, the derivative is 0. That guy gets you 3. This guy gets you, I know it's 6, but I'm going to call it 2 times 3x. And this guy is 3 times 3x squared forever, right? And if I turn this derivative into a power series, it looks like 3. Let's see. N x to the n minus 1, and it's n equals 1 to infinity. Let's see if this power series actually matches what I've just written. Now you notice I've swapped from 0 to 1 now. So when you plug 1 in, you get 3 times 1 times x to nothing. Then 3 times 2 times x to the 1. And 3 times 3 times x squared. Yeah, it matches. This guy is the derivative of this guy. So I'll put them together. Here is f of x. And here is what its derivative looks like. Can anybody see any connection?
That's just the definition of the power rule, right?
Yeah, isn't it just differentiating 3x to the n? Why did we need to drop the n equals 0 term?
Because you can't divide by 0.
For sure. That
No.
would be for integration, but
Well,
and
it would
you're right.
add an asymptote for x equals 0.
Say again?
It would add an asymptote for x equals 0.
I gotcha. It would be bad news in lots of ways. Would you agree? Also, if you plug n equals 0 into here, don't you get x to the power of -1? And wouldn't that be, as Carson was saying, a vertical asymptote at 0, which is bad news and doesn't exist. When you differentiate something, don't you lose that guy there? And that means that the n equals 0 term disappears from the equation. So we start at 1 layer. So this is a general truth that I'm now going to tell you. If you take any power series, and it's going to be an x to the n, right? That's any power series in the world can probably be written like that with a bit of effort. Then its derivative I guess I'll stick the n there, it looks nicer. Will look like that. What that means now is that I can actually do power series of the derivative of a function. And can I then take the power series of the derivative function? So if I know the power series of one function, don't I also know the power series of all its derivatives? Just differentiate, drop a term. If I did it again, wouldn't I start at 2 and drop a term? Then start at 3 and drop a term. Now, since there is an infinite number of terms, can't I keep doing that for infinity? So there is a very powerful property, and that says that if you have a power series for a function, you can also find the power series for its derivative. Is that cool or what? Now, I'm going to jump the gun a little bit, but it's kind of cool. the power series for a cosine is that. And the power series for the sine function is that. I'm just telling you that, but you can actually, you'll get to prove it in a later section. Isn't that kind of interesting that the sine and cosine functions are power series? I've already done e to the x. Remember e to the x, I did this power series. Now, if you write this guy down out as a polynomial, and then you differentiate it, can you trust me that you end up with this polynomial? So what we have actually proved here by using power series is that the derivative of sine x is cosine x. If you take a function and you find its derivative, and that power series is the same as another function you know, then haven't you found out what the derivative of that other function is in terms of the second one? That is amazing. There are functions out there, Bessel function and all sorts of cool functions, whose derivatives are now known because of this. Let's put that kind of property. Oh, almost forgot. Darn, I'm getting old. Let's have this fella one more time. Wouldn't it be nice if you could integrate a power series? And capital F of x is notation for antiderivative. So what, based on just what I have told you, what do you think the power function for an antiderivative would be if this is the original power series? Have a shot at it. What do you think you should do? Look at what you did here. Can I apply it? Well, all you can be is wrong. That's not a biggie. What do you think you should do?
Raise the power of x to n plus 1 and then divide the whole thing by n plus 1.
Would that seem reasonable? Just integrate each term? Yeah. Now, remember we lost a guy when we differentiated. I guess the question is, do I start at 0 or do I start at 1, right? When you integrate things, right, when you take antiderivatives, do you lose anything in that process? No. So you go with that. But unfortunately, don't you get a big ugly plus c? And that big ugly plus c very often is very difficult, if not impossible, to stick inside the sigma. So it's not as clean. Right? Would you agree the derivative is a clean sigma and nothing left over? But when you have a plus c at the end, how do you stick a plus c in? You know, it depends on, you know, the boundary conditions, and it doesn't always work with our fella. Okay, so here are, to finish with, 2 questions. I am about to tell you about the Robertson function. I've decided to create a power series. And we know that a power series is a function. So I can create a function, right, as a power series, right? And so my function is called the Robertson function. And it's 2 to the n, x to the n over 5. Why? Because I wanted it to be, right? That is a power function, right? That is a infinite polynomial. It's just as good a function as x squared plus 1 or sine x is, right? But I am going to find the derivative of my function. And we're going to find the antiderivative of my function. Well, let's look at the derivative. Remember how the derivative works. Remember to start at 1, right? Don't you basically just differentiate this guy with respect to x? 2 to the n and 5 don't count, they're just constants. So won't I just multiply by n and then reduce the power by 1? Are we happy about that's the power series for the derivative of my function? Okay, what's the antiderivative
Shouldn't it
of my
be 2 to the n minus 1? And
here? No, the 2 to the n is a fixed number, and so is the 5. Think of that as like 5x cubed or 5x to the square. These two don't change. Right? All you do is multiply by the power, which is the n, and reduce the power by 1. Anything else that doesn't have an x in it is treated as a constant and does not change. Right, so the 2 to the n doesn't turn into 2 to the n minus 1 or anything else, right? It stays put. Okay. Now, if you want to do the antiderivative of my function, won't the 2 to the n and the 5 also stay put, just like they did the first time? Somebody want to finish it off for me? What would the antiderivative of that guy be? Hide this fella because he's a distraction. Use that guy.
x to the n plus 1, and then multiply the whole thing by n plus 1, and then add a plus c.
Do you want to multiply by n plus 1 or divide by n plus 1?
Divide by n plus 1, I'm sorry.
And there you go. Now you might think, well, how can this help us get power series? If I know the power series of a function, for instance, don't we know the power series of that guy? The power series of that guy is him. Now, if I differentiate him, right, this guy, you will eventually get, can you trust me that you eventually get that? And if I differentiate its power series, I get that. You see, I can now find the power series of basically just by repeatedly differentiating this thing. For instance, the next one will be plus 2 over 1 minus x cubed, and the one after that, and the one after that, and one after that. So what we've done is we've found a way to expand the number of things that we can get power series for. And that's a good time for us to finish. So everybody here did get the report. I sent it out. Make sure it's accurate. I will change that 0 homework that someone mentioned, just to make sure that's accounted for. And say your last name and bye-bye.
So I might have missed it because I slept in like a minute late.
Okay.
The report you sent out included a score for the test. Is
Yes.
that our actual score?
Yes.
Sweet.
And the solution is, I believe, online. At least I've got a solution. If it's not online, I'll put it online.